particle is projected from a point P on horizontal ground. The speed of projection is 35 meters per second at an angle inverse tan 2 to the horizontal. So, here is the initial velocity vector, denoted by the letter U. Its magnitude is 35. The angle theta made with the ground is such that the tan of theta is 2, because theta is inverse tan of 2. The particle strikes a target whose position vector relative to P is xi plus 50j. Let's suppose that the target is here. So let's look at the position vector. So this is the position vector relative to P. So P is the origin. This vector is xi plus 50j. So the horizontal component is xi and the vertical component is 50j. Remember, I is a unit vector pointing in the positive x direction, and j is a unit vector pointing in the positive y direction. So they're unit vectors. That means that their lengths are 1. So if we multiply this vector with a length of 1 by x, we will get xi. And if we multiply this vector, which is j, its length is 1. If we multiply it by 50, we get this vector 50j. And if we add xi onto 50j by the triangle law, we get the position vector of the target. The coordinates of the target are x, 50. In the first question, we want to find the value of x. Now, one way to do this is to memorize the equation of any trajectory. We proved this result in the last video. So get the equation, and from the equation we can find any point that's on the curve. We know that tan of theta equals 2. We need to get cos of theta. Well, if tan of theta equals 2, we can construct a right angle triangle to find cos of theta. So we put the side opposite theta equal to 2 and the side adjacent to theta equal to 1. So tan of theta is 2 over 1, which is 2. If that's the case, then the hypotenuse must be the square root of 5. Because if we square this, we get 5, and that's equal to 2 squared plus 1 by Pythagoras. So cos theta is adjacent over hypotenuse, 1 over root 5. And what about u? Well, u is the initial speed. We need that here. U is 35. So these are the three things that we need. So we can write down the equation of the trajectory. Y equals tan theta, which is 2, times x, minus 4.9 over u squared is 35 squared, times cos theta squared. That's 1 over root 5 squared. Well, that's 1 over 5. So the equation of the trajectory is y equals 2x minus 0.02x squared. So at this point, y is equal to 50. So we just put y equal to 50. And we solve the resulting quadratic equation. For convenience, we can multiply all of this equation by 100, and I'll do a sign change as well. 100 times minus 0.02 is 2. 100 times 2 is 200. And we have to multiply 100 by 50. So we can now get the factors of this quadratic equation. This quadratic equation can be written as x minus 50 squared. So we put each factor in turn equal to 0. Well, both factors are the same, of course, so we get x equals 50. Suppose you forgot how to get the equation of a trajectory. Well, we could think of the problem this way. We're interested in the position of the object after a certain time, and we want the position in the y direction. We want sy to equal 50. The y component of the initial velocity is 35 sine theta. The acceleration of the particle in the y direction is constant. That's why we can use this formula, and it's equal to minus 9.8. So we have plus a half times minus 9.8, that's minus 4.9. We know that the sine of theta is opposite over hypotenuse, 2 over root 5. So 2 over root 5 times 35 is 70 over root 5. So we want to find the time taken for the particle to hit the target. Once we have that time worked out, we can then get x. So we need to start by solving this quadratic equation. We get this quadratic equation in t, we solve it, and we find that we just get one value for the time, because everything in here is actually 0. Now what does that tell us? It tells us that there is only one time to hit a target that is 50 units, 50 meters above the ground. So that means there must only be one target on the trajectory which is 50 meters above the ground. There can't be two. There can't be another one over here that's 50 meters above the ground. So that tells us that the target must be the maximum height of the trajectory. So I've drawn this picture wrong because I didn't know that the target was actually at the highest point of the trajectory. We would have two different times if there happened to be two points on the trajectory with the same height of 50. Then we'd have a time for this, for the particle to hit this target, and a longer time for the particle to hit this target here, which is further away. That doesn't happen here. There's only one time. Now, knowing the time, we can get x. We use this formula here for the position of a particle traveling with constant acceleration in a straight line. So we apply this formula in the x direction. Ax is 0, as I've explained to you before several times. There's no force acting on the particle in the horizontal direction. So the x component of the acceleration is 0. So we see that Sx sub x is just ux times t. But what is ux? It's 35 cos theta. It's the x component of u, 35 cos theta. 35 times 1 over root 5, or 35 over root 5. And we multiply that by t, which is the time taken for the particle to hit the target. That's 3.19. We get an answer that's very close to 50, as you saw before. The exact answer is actually 50. In part 2, we want a second angle of projection so that the particle strikes the target. So the speed is 35, theta is some angle of projection. Here is the trajectory. The target is located at the point with coordinates 50, 50, as we saw already. So let's look at the x position of the target. Well, we know that it's 50, but we know that the position s is given by ut plus a half a t squared, and in the x direction we have ux times t. Well, ux is the x component of the initial velocity, that's 35 cos theta, times t, which is the time taken for the particle to hit the target. Ax, as we know, is 0. There are no forces in the x direction. So the x component of the acceleration of the particle is 0. So s sub x, the x, that's just the x value of the target, is 35 cos theta times t. T is the time taken to hit the target. S sub y similarly is uyt plus a half ay t squared. As we know, ay is minus 9.8, so we have a half of minus 9.8 is minus 4.9. uy, the y component of the initial velocity, is 35 sine theta. So we have these two equations, and we need to solve between them to find out what theta is. By the way, sy is equal to 50. That's this distance here. So we put sy equal to 50. So we need to solve between these to find out what theta is. So we need to eliminate t between these two equations. So if we take this first equation and make t the subject of it, t equals 50 divided by 35 cos theta. This can be simplified down to 10 over 7 times the cos of theta. Now we take the second equation and plug this in for t. So we have 35 sine theta times 10 over 7 cos of theta minus 4.9 times t squared. And that equals 50. So we have an equation with one unknown in it. That unknown is theta. So what we get here is 50 times sine theta over cos theta. So we get 50 tan theta. Now, in the denominator we have 7 squared, which is 49. 4.9 over 49 is 1/10. In the numerator we have 10 squared, which is 100. So we have 100 divided by 10, which is 10. And in the denominator we have cos squared theta. Now we can write this as 50 tan theta. Actually, I'll divide by 10. So we have 5 tan theta minus sec squared theta equals 5. Okay, I'm using the fact that 1 over cos squared theta is sec squared theta. Sec theta is 1 over cos theta. So 1 over cos squared theta is sec squared theta. Now the reason I write it like this is because we can get an identity linking up tan theta and sec squared theta. We can actually write sec squared theta in terms of tan theta. So we have an equation all in terms of tan theta. So we just have the same function. So here is the identity that we use. Use this identity. Don't try to do anything else or you will go around in circles. I've just spent half an hour going around in circles. This makes life much easier. So now we have an equation in tan theta only, and the argument of the tan function is the same. It's just theta. See, we have just tan of theta here. We have tan squared of theta here, but that's okay. The angle is the same. Okay, so now we can write this as tan squared theta. If we change all the signs here, minus 5 tan theta, I will get a plus 1 here and a minus 5 on the other side. So I bring the minus 5 over. So I get plus 1 plus 5 is plus 6 equals 0. Now you see, with the same function and the argument is the same. That's a very good sign. This is a quadratic equation in tan of theta. We could even replace tan of theta with x to make it easier to read. And now we solve this quadratic equation. The factors are x minus 3 times x minus 2. Solving this quadratic equation, we get two solutions. One of them is x equals 3 and the other one is x equals 2. But of course we let x stand for tan of theta. So we get two values for theta. One value of theta is such that tan of theta is 3, and the other value of theta is such that tan of theta equals 2. This is the value that we had at the start. And this is a new value. So we have a new launch angle, theta. This new launch angle theta is such that tan of theta equals 3. The old launch angle had a situation where this point was the highest point of the trajectory, this new launch angle is a greater angle. So we could have something like this for the new launch angle. It's a greater value of theta. Tan of theta equals 3 in this case, which means that this theta here is greater than this theta here.